Hello everyone, my name is Eda Goldenberg. Welcome to Nano Open Webinar, which is organized by Sabancı University Nanotechnology Research and Applications Center. It's my pleasure to introduce my colleague and friend Clara Santato, whom I met during my postdoctoral fellowship in Montreal. Having her with us today after all these years is a real special occasion for me. Clara Santato is a professor in the Department of Engineering Physics at Polytechnic Montreal and Canada Research Chair in Sustainable Organic Electronics. Professor Santato's key achievements include seminal work on tungsten oxide catalyzed water photoelectrolysis for hydrogen production, groundbreaking work on organic electronics, especially carbon-based, specifically on organic thin film transistors. For her research on solar energy conversion and light emitting devices, she has been promoted as a senior member of the Institute of Electrical and Electronics Engineers. She demonstrated the first melanin biopigment-based supercapacitor. For this work, she was awarded the 2018 MRS Communications Lecture Award. Professor Santato is also a member of the advisory board of the National Research Council Canada and Storage Energy Hydro-Quebec. In addition, Clara is the PI of the Canada-wide Collaborative Research and Training Experience in Sustainable Electronics and Eco-Design initiative, which brings together around 20 universities and industrial partners in Canada and abroad. Professor Santato has conducted and led research projects in both European and North American institutions. Now, please let me welcome Professor Clara Santato to share with us her seminar towards green energy storage.
Hello, yes, welcome everybody. It's really an honor. I should to receive this invitation, and I should say from the very beginning that I feel at home. I have Italian origin, so Turkey is not too far, and Eda has been a very good friend since her time as a postdoc in the department, of course. I was also saying before, be kind with me. It's 6:30 a.m. So if you interrupt me with questions, you will just help me to keep a good pace and not to get asleep. So let's make it dynamic. As early as you have a curiosity, feel free to ask your question. So let me tell you a few things. So I come, of course, from the engineering physics department. And since a few years, I'm working with biosourced organic materials for electrochemical energy storage or for optoelectronic devices. I came to this type of topic after years of working in organic electronics, and then the possibility to develop an awareness about the environmental and earth impact of electronics, more specifically consumer electronics. So the accumulation of e-waste, considering the fact that there is no real design for the end of life of consumer electronics and their powering elements. Also the awareness of the fact that e-waste solid state stream is the fastest growing solid state stream now in our planet. But apart from this, I also had other elements that brought me to say, hey, here maybe the university can contribute to alleviate certain issue or to design differently. So to tackle a problem, e-waste, but also to try to prevent the problem through eco-design. So the second element important has been the energy that is embedded in the device. So the energy that is, if you allow me the word, hidden in a device, but that is used during manufacturing, okay? So two elements, and how we try to answer. Let's see, our root that I really care about this. Our root is just one of the possible roots. We are used to say that for a global problem, you have several solutions that have to complement one to the other. So you're not in competition. Our root is the possibility to use organic biosourced materials. And we will see why, the strength and the weakness of this type of materials, and then the device that we build with them. Before I go straight on the problem of, so electroactive biosource material, I would like to tell you something. The environmental awareness, the earth issue awareness, come also with another type of awareness, that is the fact that, again, I mean, this e-waste issue is a global problem. So you have countries that use, fabricate and use, and countries that, honestly speaking, we could use the word of the United Nations University, and so the report that we have mentioned here in this slide are really used as dumping sites. So this brought me, it's about 10 days. We submitted the full application to UNESCO for a UNESCO chair in green and sustainable electronics, where Canada can collaborate with countries like Ghana and Nigeria, but also other countries like Senegal, Burundi, South Africa, and Tanzania on the issue of e-waste, but also, especially with Tanzania and Burundi, eco-design. If after you're curious, I'll be here during the seminar, after the seminar, in the weeks to come. No way, we're here, and this is a long-term project. So if we go more into the powering element for electronics, we should say at the beginning, and the way, again, interrupt me whenever you see that something is not careful, rigorous, or that I miss a certain point of view. Please share with me. These are subjects so evolving so rapidly in these days that we really need to be awake and collaborative. This is my point of view, at least. So the batteries, the supercap, the accumulators are not, for the moment, considered as part of the e-waste. Despite this, very well described, in my opinion, in a chemical review very recent by Professor Philippe Poiseau in Nantes, so in France, we have a set of environmental and not only environmental issues with batteries. I just brought here two examples. The use of toxic organic electrolytes, for instance, but these are just to extract out of this radio. So we could discuss about other aspects, of course. Or, as we were saying before, for the electronic device, the energy that is used during manufacturing. So we try to go for green chemistry principles to be respected during the choice of the materials and the choice of the process to make, anyway, greener the powering elements of electronics. Now, when I use greener, I know that is a kind of a frustrating word. We like to measure. I always tell to my students, give me the dimension, give me the order of magnitude. But when it comes to green, it's really not easy. So I would say it's not to be to run away from the problem, but I think we need a certain degree of humbleness. If you want, we can improve the practice, we can develop the eco design, but measuring is for the moment maybe a bit too ambitious and not always realistic. Of course, we can avoid the use of certain elements or certain processes. Now, I don't know exactly what is your point of view, and again, welcome. The sharing will be absolutely welcome. But when we talk about batteries or anyway, powering elements, of course, we come, all of us, I think we have in our minds also the extraction of certain chemical elements and the conditions of the workers for the extraction, for instance, of cobalt in the mines of the Democratic Republic of Congo. So in this sense, you see how the issues are connected. And here, I think it's the need to have a complete life cycle analysis in our fields, in the fields of storage, like in the fields of consumer electronics. So I think you and the students, and so in this sense, the Create Seed program that Ada was mentioning. So really the need to have an holistic view from the selection of the materials to the process I adopt to the performance, technical performance of my device to its end of life. So now I think we really have to have this including view on the device, as I was saying. In this sense, the use of carbon-based material could have an advantage, could have an edge with respect to other elements, in the sense that, I mean, carbon is abundant. No geopolitical issues involved in retrieving, I mean, in obtaining carbon-based material, relatively low cost, and the interest would be also, if you allow me, to get this carbon from waste, from forestry industry waste, from food waste. This is the way where we try to go now. At least this is the way in which, I mean, the two cases of study I will show you now go. So in this sense, we talk about sustainable organic electronics. And I would add the main concept for us, the dream on the long term would be to biodegrade the device. So to really put the device in an industrial compost following international standards from, for instance, ASTM, no more, no less than this. Now, as I was saying at the beginning, no competition with other type of elements, formulations, and processes. I think we just explore several routes that complement each other, that could be good in a context instead of another one. We propose our route. And then we will see. But it's really not a matter of I'm better than you. It's more let's complement each other towards a green solution, greener solution. Now, when you say organic electronics, a bit different is the question for organic electrochemical energy storage. When you say electronics, you mean molecular structure that feature conjugation. So an alternance of single and double bonds. These alternates of single and double bonds give you the abundance of electrons that give to your organic materials an electrical response that is non-trivial, that is not the response of the protective cable for a copper wire, just to understand each other. Okay, so the field of organic electronics, I don't know how many people in the crowd are familiar with, but in 2000, the Nobel Prize in Chemistry has been awarded to the discovery and then development of organic conducting polymers. So the first conducting polymer has been doped polyacetylene. And at this point, I think we have really a myriad of small molecules or polymers with this conjugated structure that have been used in photovoltaic cells, in light emitting diodes, in organic thin film transistors, in sensors, chemo and biosensors, or also neurological implantable electrode, considering the softness and the ion permeability of organic electronic polymers. Okay, I think we could go back to this slide at the end of the talk. Now I would like to go ahead, but because this is kind of, it shows the if you want, the multidisciplinarity of the field, but I don't want to lose too much focus. So do you have questions for the moment, for this general introduction? Would you have some suggestion, or can I go ahead as you prefer? We keep going?
Yes, we go on. If we have any questions, we can write in the chat, and later on.
Perfect. Perfect. Okay. So the two cases of study I will discuss today are about melanins, so the melanin biopigment, and tannins, the tannins that we find in the green tea or in wine. And melanin is what color our skin, for instance, one of the form of melanin. Don't mix up, please, melanin with melatonin that we take when we could travel and we have jet lag, or melamine, that is of course an insulating form, an insulating plastic that we use, for instance, dishes for camping. So nothing to do. This is melanin, and it has a conjugated structure. So now, what does melanin and tannins have in common? I would say my point of view in the specific context of this presentation is the fact that they have catechol group. So you will see this 2OH group in the benzene ring that belongs, for instance, for the melanin, to the pyrrole, to the indole structure, so condensed pyrrole benzene. So the presence of this hydroquinone, quinone redox couple is actually the key to their to the possibility to exploit them in electrochemical energy storage. Okay, so you have in the top scheme the redox activity, electron transfer accompanied coupled to proton transfer for the indoles that are the building block of melanins. We will go a little bit into details in a few seconds. And you have the hydroquinone, quinone form for the tannins in the lower scheme. Okay. Of course, when you think about electrochemical energy storage, you need materials that feature charge transfer processes, of course, but you also need to have ionic transport. So these are soft materials, carbon-based materials, so they are permeable to ion transport, okay, permeable. But there is also something that is extremely interesting to me, that is the fact that this catechol group, and in a certain extension also the quinone redox form of the same group, they can chelate metal centers, so metal cations. Chelate, now I don't know how many chemists are in the crowd, how many material scientists, how many physicists, how many electrical engineers, but chelation is just an interaction between two chemical species where you have the donation of electrons from, for instance, a ligand, in this case the indole, or the catechol group more specifically, and the electron deficient metal center. So you see that you add a color to your to the ionic transport. Actually, I would not take this topic back today, but it's interesting, I think, to observe the fact that this chelation come with the possibility to interact with multivalent ions. So, okay, we can work in sodium or just in an acidic electrolyte or in a sodium-containing electrolyte, lithium, but also multivalent ions. And here I just anticipate maybe even with biological relevance. Okay, so if I go a little bit into the detail of this melanin, it's interesting to see that the melanin is a big family of pigments, and eumelanin is what color our skin. We have it in our eyes, we have in our hair, we have in the inner ear, we have in our tongue. So it's in all our organs of sense. And we also have melanin in the form of neuromelanin in our brain, where actually you have core shell structure of pheomelanin, core of pheomelanin, that is yellow reddish, and then a shell of eumelanin, that is a brownish pigment. So you see how I think even from the training or strictly research without thinking about applications, things are extremely interesting, because you have redox active materials that are intrinsically biocompatible. So I think that when you study, for instance, the function of neuromelanin in the brain, you can learn something about technologies, that we want to develop. I will not talk about this today, but I'm starting a project on really the bio role of neuromelanin. Neuromelanin is in charge of controlling the fluxes of metal ions in our brain, and as such, it is involved in neurodegenerative diseases like Parkinson's disease. Anyway, for our purpose, let's say that we understood that is melanin, that it's a biopigment that has an electronic conjugated structure that can undergo electron transfer, proton-assisted electron transfer, actually results from the coupling, from the polymerization of two main building blocks that are here in this green rectangle. So the hydroxyindole, or the carboxylic functionalized hydroxyindoles. This is an interesting material, I would say, and you might be very young, but in the 60s, in the 70s, there have been reports on the amorphous semiconductor behavior of pressed pellets of powder of melanin. And so, look, this is very curious, because people reported in Science, at least 2-3 seminal papers in Science about the threshold switch. I don't know if you see this bottom line plot. So you have current versus applied potential for pressed pellet of melanin of different thickness, 0, 1, 1, 10 millimeter. And here, so they observe this electrical switch that is usually, featured by amorphous semiconductor. So you have to know that the first report of organic electronic materials that brought to the Nobel Prize, I already discussed, has been in 1977 with a publication in Chemical Communication. So here we are a few years before, with people already talking about the possibility to have a non-trivial electrical response, not only in an organic material, but also an organic material that is present in living organisms, okay? So, human beings for sure, animals, but also spread flora and fauna anyway. So I think this is curious. We have a very intense research on the electronic transport of biopigments. I will not mention today, but if you are interested, I think there is at least 1/3 of the group working on this. So on the electronic, not ionic transport of these biological materials. Anyway, let's focus on tannins and on melanins for their electrochemical energy storage. I think it's since yesterday there is available an article online on our preliminary on the exploration of tannins, and in our specific case, tannic acid and the enantiomer plus catechin for electrochemical energy storage. There are not too many reports. There are anyway 1-2 meaningful reports, especially from the National Renewable Energy Lab in Golden, Colorado. So with a system based on iron tannins for storage, we wanted to go as simply as possible. So without any redox metal in our formulation, to try really to study now the charge transfer processes in our organic materials. So we really wanted to have solutions and then drop cast solution on the current collector, and that's it. So we are taking the systems as simple as possible because we really want to understand the intrinsic properties, and then from there we build and we make a complex system. But we also have a very if you allow me the expression, a very fundamental teeth here in the group. So we really care a lot about the fundamental aspects of phenomena. And so I wanted really the students to have the simplest possible system to study. So here you see two SEM images, but we will have many more after, of solutions of tannic acid or catechin on carbon paper. And then the cyclic voltammetry is obtained with the different loading of the materials. Now, I would really not stop too much because, okay, this has been published, but in the meanwhile, I will show other results that are much more interesting than this. I think in a few months we did a good progress. So I just mentioned this. This was kind of seminal work, but then the students were very active, and so we really improved the performance of the storage. So I would not stop too much. I want to just draw the attention on the molecular structure, in the sense here we have, for instance, the structure of the tannic acid. I don't know if you know maybe tannic acid, maybe okay for the wine or for the tea, but sometimes it has been used as simply as a binder without thinking too much about the redox properties. In any case, it has so this glucose center, and then you have esterified gallic acid units, and then esterified gallic acid end group. So it's a kind of complex molecule. Still, we could call it small molecule, but complex and with its importance and symmetry anyway, that we should not forget. So let me tell you something. This is two slides are really key for me. You always complain, and in this sense, the review of Professor Poiseau that I was mentioning at the very beginning, so if people are interested in organic electrochemical energy storage, they should read this chemical review 2020, written by Philippe, that, for instance, the cycle stability of organic electrodes is not really wonderful. So I think, at least my intuition is that what is extremely important is the interface between this organic redox material and the current collector, where you collect the electrons that you extract, that you inject, of course. So we worked a lot, and here the students, so what we have under review now, I think it's really important. We worked a lot to improve this interface. So we start with commercial carbon paper, but I think the student was very good in modifying through a chemical thermal treatment, using bath of nitric and sulfuric acid, was very good in essentially increasing the surface area of the fiber of the carbon paper, and not only increasing the surface area, but also surface doping the fibers. Surface doping, as you see from this EDS or EXPS analysis, not too well resolved the spectra of EDX. I see it's a bit small, but in any case, so you can find nitrogen and sulfur on this on the surface of the carbon paper. So surface area and doping bring two things. So the possibility to increase the loading of the organic redox material, an improved wettability with respect to aqueous electrolytes that are the electrolytes of primary interest for us, and also a faradic activity. You could think that current collectors, they just work in following an electrostatic mechanism. But this doping adds to the electrostatic mechanism the charge transfer mechanism to your carbon paper fibers. Okay, so charge transfer, Faradic, I use it as a synonym. So it's clear that when you have an electrode, and an electrode made with our, for instance, Quinone-based biosource material, this Quinone-based have to be deposited over a surface, a conductive surface. I call this second portion, if you want, second component of the electrode, the current collector. Sorry if I'm trivial for the electrochemist, but I think the participants, so we have a broad background here, and so I try to avoid technicalities. Now, on this modified carbon paper, we deposited our melanin A and C figures, or tannins B and D. And let me tell you something. So, of course, a different magnification here of the images, if you go top to bottom. But what is important for me here is the fact that you see this little sphere, very dense of melanin on the carbon paper in the figure C, so top, bottom left, sorry. And on the right, bottom right, you have the tannin modified carbon paper. So here, for tannins, we had to stain. So I don't know how familiar you are. Me, before working with this material, I was not anyway. So you want to reveal an organic material on an organic on carbon, not trivial with scanning electron microscope. So we needed to stain, a word that I usually associate to optical microscopy. Anyway, we stain in our early days with heavy atoms, and so uranyl salt. In this case, the tannin was stained with silver nitrate solution. Now, the interaction, how you block the heavy silver atoms, is there is a kind of a debate in the literature, but it could be chelation, so the process I was mentioning before, or even really chemical reduction. So you have silver atoms that reveal where the tannins with its chemical reduction properties is located. Okay, we could maybe discuss more later, but for me this is extremely important. Again, so the interaction Quinone metals, it's important for me, as I was saying to you before, for the electrochemical energy storage, but also for the studies we are doing with the neuromelanin. So I try always to keep these bridges open, if you want. Anyway, with this treated carbon paper, so carbon paper that is now with an improved wettability, with Faradic activity, without Faradic activity prior to deposition of the Quinone-based material, and with an higher surface area to host more quinones, we went to characterize, of course, the electrodes, single electrodes at first, and then we built symmetric supercapacitors. Now, this is a study that is under review in this moment. I should say we have good expectations. On top, the melanin, if I have to detail, it's Eumelanin, so it's not the pheomelanin, it's not a neuromelanin. When I call it tannins, this for me, it's the catechin. We saw earlier the molecular structure stabilized by tannic acid. Tannic acid has a poor redox activity, as I was saying before, and it's used here just as a binder. So we did, I will have a synoptic table in the slide to come. So we did a complete characterization of this symmetric supercapacitor, symmetric, where the two electrodes are actually the same type of electrodes immersed in an aqueous electrolyte. So this is sodium sulfate, pH is quasi-neutral. And so we did the complete characterization in the sense of, so the cyclic voltammetry, current versus voltage with respect to a reference. This is for the single electrode. Sorry, here you have just the supercap, so the voltage difference between the two electrodes, the charge discharge curves. And areal capacitance with respect to the current density. If you go, they are really symmetric pictures here. So we have the capacitance retention versus the cycle number. You'll see that here we explored 5,000 cycles, and then so the electrochemical impedance response and the Ragone plots. So I have at least two elements to rise, and I think they are maybe more for the discussion, for the question and answer than really here in this moment. So I would draw the attention on the charge discharge curves, on the stability, but also on the cyclic voltammetry, if you want. So these supercap are somehow, we call them pseudo supercap, in the sense that they have a Faradic activity due to the presence of the quinone, and if you allow me, even to the modification of the surface of the carbon, but they have kind of a box-shaped cyclic voltammetry that is typical of capacitors that behave following, an electrostatic mechanism. For tannins, of course, the diffusion limited signals are a little bit more developed, but I would use the expression pseudo supercap to interpret the behavior of our device. You will see here that just one slide of performance then for interested people, otherwise I will go ahead. So we have for our melanin this 277 milliwatt centimeter square, or if you prefer, normalize over the weight of the electrode. So when you have, so we normalize over the area, we normalize over the mass. The first set of values are for the eumelanin, the second set is for the tannin. So we have here the maximum energy density, and again for the melanin and for the tannins with an 100% coulombic efficiency. Is if you compare this with the state of the art, and I would have available the draft of a review we are writing right now, I think we are well positioned, especially if you compare to the fact that we have just an aqueous quasi-neutral electrolyte. And sometimes what we found in the literature with similar performance was more lithium perchlorate in acetonitrile, or like I'm showing now, PDA H2SO4, or electrolyte that are not as friendly as those that we try to use. And I don't know if it was clear, but we have a wide working potential window here. So 1.6 in the supercap, but you can explore up to 2.2 volt actually for the single electrode. So I think I delivered, one of the two key messages I wanted to deliver. I just tell you that these last results that I consider pretty interesting, even from strictly speaking a technical point of view, they built on years of research where we explored, the behavior of this biopigment. Look, the first time the group entered the field of melanin from the door of transport physics. So for me, I thought with the students, with colleagues, you want to study transport, that is a sequence of charge transfer processes, you better study charge transfer at first. This is why we attacked the electrochemical, we adopted the electrochemical perspective. And so a few years ago, the first cyclic voltammogram that we observed with this box shaped already told us a lot. For people a little bit more in electrochemistry about the pseudocapacitive behavior, for me, it was not only a pseudocapacitive behavior, but I added also a second possible interpretation. That is the fact that your box shape could come from the convolution of redox sites that are actually different in their energy. So you have, if you want, a featureless box shape voltammogram because you are convoluting different redox signals. Okay, here we could really discuss. This is really research, I think. I cannot say I'm right, you're wrong. Here we could discuss and we could have different contributions. So maybe nobody's right and nobody's wrong, but it's just a complementarity of visions, if you want. And what in my mind I did is to associate this convolution of different redox sites to something that is completely different, to the optical absorption spectra of this biopigment. Usually people that is here on the left, bottom left. This is the optical spectrum of the biopigment. Actually, when a person knows about melanin, is because we tan in the summer, we clear in the winter. People that were born close to the equator line, they are darker than other people for protective reasons, and that's it. Here, this spectrum has been interpreted. You see that it's featureless, and it goes from the near infrared to the UV, really featureless. So the best physicists in the melanin fields, and among them for sure, Professor Paul Meredith, for years in Brisbane and now in Swansea, so in the UK, Paul suggested the possibility to have a convolution of different chromophores in the material. How it comes? It's a molecular material, you could say. How it comes? You have to have your nice absorption peak. It comes from the fact that these materials, natural materials, are beautiful because they can be low cost, they can be abundant, but they come with the chemical and physical disorder. So we have to be aware from the research, scientific point of view, that they are extremely difficult to study. That's the truth. I see my students, I know how many years it takes to have a conclusive result. So I would associate anyway the featureless voltammogram to the featureless optical spectrum. I think there is something true in this association. Again, we could discuss. Anyway, the optical absorption spectrum of melanin brought us to think about the possibility to, if you want, electrochemical dope and photodope the materials. So very recently we reported on a light-assisted supercap. But before this technological development, let's say something, because we always have to keep alive the excellence in research and then the, I think, technical and environmental performance of the technologies and devices that we develop on top of this knowledge. You know that is a disordered material. So this is the scientific challenge. Now, what do? You try to engineer, I think, the material. You try to simplify it, to understand what is, for instance, the nanostructure, what is the supramolecular assembly that brings you to a certain functional properties that one day will bring you to a certain device performance. So we work with organic synthetic chemists, and we were able to disentangle, if you want, to study one building block at a time. So we said at the very beginning that this melanin comes from the coupling of two building blocks, the indole and the carboxylic indole. So here we ran the cyclic voltammetry of samples based just on one of the two monomers. And actually you'll see that the current that we obtain just with the DHI, so without these disturbing terminal groups that disrupt the supramolecular assembly, the current are really much higher than when you have the DHI-CA. So we learn a lot. We learn a lot in the sense that, yes, okay, we might be disordered, we might have a convolution of redox sites in the voltammetric response, but we can also engineer the material in collaboration, of course, with organic synthetic chemists. We can select one of the two building blocks with a very interesting solid state polymerization rules. We fabricate samples that are preferentially constituted of DHI or DHICA, and we start to learn what happens within the materials instead of being blind and just looking at the voltammetric response, that it's of course a macroscopic response. So what is interesting in these materials is that, and this is, if you want, for the moment, throughout all the field of organic electronics, how you keep up your molecule, how you go from the molecule to the material. Usually you go through a pi-pi stacking, okay? So the pi orbitals stack, and the electrons can travel through these overlapped orbitals. Actually, this overlap generates bands. Quasi bands, if you want. You could establish an analogy with the bands of inorganic semiconductor. So if you have the DHI, you can have really relatively intuitively speaking, affordable. Anyway, pi-pi stacking. If you have this lateral COH group, things are much more complicated. And of course, the quality of the stacking is lower. And as a consequence, you expect a weaker electronic transport, as it's the case for our voltammetries, where we saw that the current with the DHI is slower than the DHICA. So I am associating now the voltammetric current out of these electrochemical measurements to the electronic transport in the film. Okay, in any case, so I think we said something. We have this Quinone based material. They have the redox activity. We can exploit to develop technologies and devices the Quinone activity, of course, after paying a lot of attention to the interface with the current collectors. We have to be, I would say, from the scientific point of view, go slow in the sense that you have to deal with chemical and physical disorder. I would love to talk to you, but during the question time, otherwise the talk is too long and this is not a good thing. And now we said, with this disorder, maybe you can tackle, you can investigate engineering the materials, adopting one building block at a time, and then you understand things slowly. It might look a little bit too reductionism approach, but I think there is something good in this. Maybe it's not the absolutely best approach, but there is something good in this. In any case, we always have an instinct. I mean, we are an engineering school. We always have the instinct to go also applied, to give a function to apply, to give an impact to our findings. And so we kept in mind this optical absorption and this wonderful matching with the solar spectrum. So we, as I was anticipating, we try to explore, hey, what happens if our supercap are exposed to a solar simulator? Actually, things worked pretty well, in the sense that so we really exposed to the solar simulator DHI-melanin, so synthetic melanin that emulates the Eumelanin, so our skin pigment. We repeated this experiment one building block at a time. And for instance, for the DHI melanin electrodes or samples, we were able to have a power density increase of about 56% in presence of solar light, or and a maximum energy density increase of 18%. So now, again, I will not develop here, but I kind of invite, but very humbly, I know how busy we are, and how to read this paper. And I would have to tell you that even now we are not, if I have to be honest, as I hope to be, even now it's not trivial to know if it's a pure photophysics effect. So with the excitation, we just simply increase the density of the mobile charge carriers in our material, or if we have a little but local, not macroscopic temperature effect. We don't have macroscopic because we follow very carefully the temperature of our cell, of our electrolyte. but at the angstrom scale, I cannot answer for the moment. Or even the energy of the solar light could induce a favorable supramolecular arrangement of the pigment. So we're still working on this in collaboration with the group at the Ohio State University, so Professor Ben Kohler. So we hope to have a mechanism that is more, that is clearer in 1-2 years from now. And in any case, this light-assisted electrochemical energy storage will be one of the concept the group is gonna keep for the years to come. For the choice of the electrolyte, for sure, I mean, we put ourselves a little bit of a boundary in the sense Clara decided to go in aqueous media or in hydrogel, in really friendly hydrogels. And there is anyway a foundation to go slightly acidic most of the time. And the fact that with this material we go slightly acidic comes from the very favorable proton transport properties in this material. There is a group. I invite you. You could, for people interested in biomolecules, biomacromolecules, I would say bioelectronic devices, environmentally friendly organic electronic device. I invite you to follow the work that Professor Rolandi is doing at the University of California in Santa Cruz. So with this group, we really measured the protonic current in our films. You can, with palladium hydride protons, measure the protonic current in materials when you use gold to measure the electronic current. So anyway, the favorable proton transport properties brought us to select acidic aqueous electrolyte for our electrochemical experiments. I will not go into the detail, but very happy to explain everything concerning the experimental configuration or the sense of this palladium hydride and its transparency to protons. The very last, and sorry if I'm extremely slow, I didn't think, the very last experiments deal with a collaboration with a group at the Canada National Research Council on the compostability of our organic electronic materials. So I will just, this Nature Communication article is just in press in these days. So we just put in an industrial compost our melanin, so our electronic biosource material, with a negative reference like polyethylene, a positive reference like cellulose. We follow the international standard ASTM 5338. We follow this compostability with this standard. Not only we had the positive negative reference, but we also put in the compost synthetic organic electronic materials, and actually we observed the higher compostability of the biosource material with respect to the synthetic. Higher, but still not perfect as we like. And we attribute, again, to the self-assembly properties of the melanin, the inaccessibility, if you want, to enzymes. So to the enzyme, and so to the bacteria, and then the enzyme that are supposed to metabolize the material. And so here again, you see how the super applicative studies are connected to super fundamental studies on the self-assembly properties. In this sense, so I'm working now with a scanning tunneling microscope to study the molecular disassembly, but I will not talk about this project today. What I can tell you is that students, more with an atomic force microscope, are working really on the nucleation and growth of these thin films to study the self-assembly. And if you study the self-assembly, you can even get insight on the disassembly that is needed once you are in compost condition to degrade your material. Okay, so sorry if I've been a bit too long. Main concept for me is the use of biosourced, so extracted from natural sources, organic materials that are redox active for a possible green, in the sense of green principle and biodegradability at the end of life, energy storage. The interest in coupling the different possible function of a material to show multifunctional devices like light-assisted supercap and compostability. Now, what are we doing I think I would say next 2 to 5 years is to extend the library of biosourced material. My dream, the second dream, would be to work with microbiologists to tailor the quality of our compost for our device. For the moment, compost is optimized for insulating organic materials. We have conducting organic materials, and we have devices that include metals. So the compost has to be engineered, and then maybe one day compostable integrated circuits. Here I stop, ready to take whatever questions. As I was saying, maybe now or in the days to come. We are here, and no rush at all. This is so serious and I would say challenging science. So we know that these are long-term projects. I should, of course, acknowledge the funding agencies that trusted our idea. I hope we are rewarding them. And I should say we have all kind of possible support for visiting scientists, for graduate students, undergraduate students within the context of different programs like, the Create Seed or the Canada Research Chair, or I guess pretty soon the UNESCO Chair. So we really welcome any type of collaboration. For the moment, maybe virtual, hopefully in a few months from now, we don't know, in a few months from now, face to face. So you would be always welcome to visit us for sure. Thank you very much.
Thank you very much, Clara, Professor Clara Santato. We thank you very much for your interesting presentation. Is there anyone has question? Okay, I can ask one question. I'm not a chemist, and actually Eumelanin, Tannin are far from me. I'm more in inorganic world. But my question would be, if you compare your supercapacitors performances, how you could compare today's non-biodegradable devices, and what are the challenges? You mentioned several problems, but basic challenges. Who would like to work on this field?
Yeah. I think what I mentioned, so I would say the cycle stability, and so really, in my opinion, is really preparing the interface between the current collector and the Quinone-based material. This would be it's really the main challenge. And then, of course, when you look at this polyphenol, maybe also the catechol density. So how many phenols that are the redox active group do you have per gram of material? So we have to be good in loading active materials, and they have to stay on this interface. And being disordered, so you say these are the two things actually, interface and disordered. Being disordered, this means that electronic transport is not very efficient. This means that the loading cannot be as high as you wish. So this, I think, it's the main problem, the fact that the disorder brings weak electronic transport, so you really have to engineer at the nanoscale these materials. Yes. So a lot of this is why, here there is a lot of electron microscopy, a lot of spectroscopy to understand how the molecules are arranged. This is really not trivial.
Okay, thank you very much. Is there any question we can take? If not, we are afternoon. So we thank you again and
Thanks to you.
keep in touch.
Yes, of course, Ada. We can, if you want, we can spend a few minutes on the phone after.
Sure.
This is personal. Okay, thank you. Bye, bye, bye.
Thank you, everyone.